Okay, so for decades, one of the first things you learn in machine learning, it's practically dogma, is that you have to avoid overfitting. We're all taught that making a model too complex is a recipe for disaster on new data. But what if that's just not the full story? What if in the world of today's massive neural networks, that fundamental rule doesn't just bend, it completely shatters? And what if, get this, the more you overfit, the better your model can actually get? Well, this is the double descent paradox, and I promise, understanding it is going to change how you think about generalization.
So here's how we're going to unpack this whole thing. First, we'll look at the classical story and pinpoint exactly where it falls apart. Then we'll zoom in on this weird spot called the point of rigidity. After that, it gets really interesting. We'll dive into the unexpected freedom you get with over-parameterization, uncover this elegant idea called the principle of laziness, and finally, we'll put it all together into a brand new intuition for how these models actually work.
All right, let's start at the beginning. What's that core rule we all got drilled into our heads in our first stats or ML course? Right. It's always been pretty straightforward, pretty intuitive. If you give your model too much capacity, too many parameters, it's not going to learn the real signal. It's just going to memorize every little quirk and bit of noise in your training data. And this U-shaped curve, this is the mental picture we all have. It's the classic bias-variance trade-off. On the left, your model's too simple, so you have high bias. On the right, it's too complex, and you get high variance. The sweet spot, we were always told, is right there in the bottom of that valley. It's all about finding that perfect balance. For the longest time, we all figured that's it. That's the whole picture. Nobody thought to just keep pushing the model capacity way, way further to the right. But then deep learning came along and did exactly that. And what researchers found, well, it changes everything.
And here it is. This is the full story. That classic U-shape is just the beginning. As you keep cramming more and more parameters into the model, the error doesn't just level off. It hits this crazy, often catastrophic peak, and then it starts going down again. A second descent, often leading to a final error that's even lower than the so-called sweet spot from before. This is the double descent phenomenon. And to solve this whole puzzle, we've got to understand what on earth is happening at that peak. So let's zoom in on that peak. It's easily the weirdest part of this whole graph. Why does the model performance get so spectacularly bad right at that one specific moment?
Well, this peak happens at a place we call the interpolation threshold. Think of it as this incredibly precise critical point where your model has exactly enough parameters to nail every single training data point perfectly, not a single degree of freedom to spare. And that's the core of the problem. When you're that perfectly constrained, your model has absolutely zero freedom. At this threshold, there's only one possible mathematical solution that can check the box of hitting every single data point. It's completely locked in. And as it turns out, this one unique solution is almost always awful for generalization. Imagine I give you a bunch of scattered dots on a page and tell you that you must draw a single line that passes through every single one. You'd have to make these really sharp, unnatural turns, right? Your line would have to zigzag all over the place. That's what the model is forced to do. It creates this brittle, high-energy, high-variance function that's terrible at predicting anything that isn't one of those exact dots. That's what we mean by rigidity.
Okay, so that explains the dangerous peak. It's a point of total rigidity. But what about the magic that happens right after? Now we're entering the truly modern regime, the world of over-parameterization.
The second we step past that interpolation threshold, everything changes. We are now officially in the over-parameterized zone. We have way more knobs to turn than we have points to fit. The model is no longer stuck with a single unique solution.
And this brings us to the absolute core of the mystery. If there are now literally an infinite number of functions that can perfectly fit our training data, why does the model choose one that's good? Which one does something like stochastic gradient descent actually settle on? And why does that particular solution generalize so well? Well, the answer is just beautiful. It's an elegant, implicit bias that's hiding inside our optimization algorithms. You can think of it as a principle of laziness.
Now, the technical mathematical term for this is the minimum norm solution. But the intuition behind it is incredibly simple. Out of all the infinite possible functions that could connect the dots, the optimizer is biased towards the one with the smallest norm. And what that means intuitively is that it picks the smoothest or laziest function possible, the one that does the absolute least amount of work to get the job done.
Here's an analogy. Imagine your function is a physical object, like one of those flexible splines that architects use. If you pin that spline down at all your data points,
The shape it naturally settles into is the smoothest possible curve that connects them. It takes the path of least resistance. That is exactly what our over-parameterized models are doing. They finally have enough freedom to just relax into their lowest energy, most natural state. So why is this lazy solution so good? Well, by picking the smoothest path, the model is essentially regularizing itself without us telling it to. It avoids making up wild, complicated wiggles in between the points it knows about. And it's this inherent smoothness, this lack of unnecessary drama in the curve, that lets it generalize so incredibly well to new data. It has found the absolute simplest explanation that fits the facts.
So, let's put this all together. With these two key ideas, rigidity and freedom, we can build a whole new, much more complete picture of what generalization is. Just look at the contrast here. At the threshold, the model is rigid. It's forced into one and only one high-energy, jagged solution. The result? Insanely high variance. But beyond the threshold, the model has freedom. It gets to choose from an infinite sea of solutions, and it picks the laziest, smoothest, minimum energy function. The result? Surprisingly low variance. So the whole story of error from left to right looks like this. First, in the under-parameterized region, your model's just too simple. It's biased. Then you hit that interpolation threshold where the model's rigid, constrained, and forced into a horrible, spiky solution with high variance. But then, as you keep adding even more parameters, you give the model freedom, the freedom to be lazy. And it uses that freedom to find the smoothest possible fit, which just happens to be fantastic for generalization. Which means this term we use, benign overfitting, is, well, it's kind of a misnomer, isn't it? It's not really overfitting in that classic sense of just memorizing noise. It's actually a direct result of giving a model so much freedom that it can find the simplest, smoothest explanation that's consistent with all the data. It fits the data perfectly, sure, but it does it in the laziest way imaginable. And that leaves us with this really fascinating, massive open question. This laziness, this preference for the minimum norm solution is an implicit bias. We didn't explicitly program it into our models. It just emerged from the training process. So it really makes you wonder, as we build these ever larger, ever more complex models, what other good biases, what other secret sauces are hiding in plain sight, quietly guiding these systems toward solutions that are far more effective than we have any right to expect?